Here we continue our discussion with geometric optics. Thin lenses are used to visually examine organisms in biology and stars by astronomers. In this section we will discuss lenses and the common lenses that we are using. First we talk about thin lenses. Thin lenses are characterized by having two lenses that are combined together where their focal lengths are equal. Here we have the thin converging lens where it has an appearance of a rice seed. As light rays hit its surface, the light converges on the other side. The other one is the thin diverging lens. When rays of light hit the surface of a diverging lens, the light diverges out. Here we have a simulation of a thin converging lens. As you can see, the image size and position alters when we move the object on one side. As observed, the light passes through the lens since it is a transparent material. Let us examine the different rays present for thin lenses. First we have the parallel ray. It is drawn parallel with respect to the optical axis, then intersects the second focal point as shown in the figure. Central ray is drawn through the vertex and does not deviate as it passes through the other side. We see how it behaves as shown in the image. The ray simply passes through the lens and intersects the center of the thin converging lens and the optical axis. Focal ray is drawn through the first focal point and then emerges parallel to the optical axis. The image is determined by the position of the rays where they intersect. Here we see that it is positioned on the right side of the lens and it is on the same side as the outgoing light. Let us look at the sign convention. The distance s is positive here because it is on the same side as the incoming light. The object is considered a real object. The image distance s' here is positive since it is on the same side as the outgoing light. The image is considered as a real image and it can be projected onto a screen. Here we have the formulation of the thin converging lenses and it is given by equation 1 and equation 2. This is the same equation as the one we used for mirrors. Sample problem on thin converging lenses. A candle is placed at a distance of 30 cm from a converging lens having a focal length of 10 cm. For letter A, at what distance from the lens the candle's image is formed? For letter B, is this image real or virtual? And for letter C, is this image upright or inverted? First we draw the problem and here we represent the candle as an arrow in an upright position. We added the arrows to roughly determine the position and orientation of the image. For letter A, the distance of the image is determined by using equation 1. We rewrite this to solve for s' and get that it is positive 15 centimeters. We see that it has a positive value which indicates that it is on the same side as the outgoing light, and this agrees with our graphical representation of the problem. For letter B, based on the figure, since the image is on the same side as the outgoing light, then it is a real image. And for letter C, based on the figure, since the image has a reverse orientation with respect to the object, then it is an inverted image. Here we have a simulation for thin diverging lenses. As you can see, when an object is moved, an image is created and it is dependent on the position and orientation of the object. Here we examine the rays present for thin diverging lenses. The parallel ray here is drawn parallel to the optical axis, then diverges with an angle with respect to the second focal point. Central ray is drawn towards the vertex without deviation as shown on the figure. Focal ray is drawn towards the first and moves parallel with respect to the optical axis. The image position is determined by the point of intersection of the rays. We see that it is positioned on the left side and it is opposite the outgoing light. The object distance s is positive here since it is positioned on the same side as the incoming light. And this object is considered a real object. The image distance s' here is negative since it is on the opposite side as the outgoing light. This image is considered a virtual image and it cannot be projected on a screen. The equations for the distances and magnification is given by equations 1 and 2, which is the same for the thin converging lenses and curved mirrors. Here we have another problem. A diverging lens of a focal length of 10 cm can form an image of an object 20 cm away from it. For letter A, what is the location of the image? For letter B, is the image real or virtual? And for letter C, is the image upright or inverted? And find its magnification. Refer to the figure below. For letter A, the distance of the image is determined by using equation 1. We rewrite this to solve for s' and get that it is negative 6.67 cm. We see that it has a negative value, which indicates that it is on the opposite side as the outgoing light, and this agrees with our graphical representation of the problem. For letter B, based on the figure, since the image is on the opposite side as the outgoing light, then it is a virtual image. And for letter C, based on the figure, since the image has the same orientation with respect to the object, then it is an upright image. Using equation 2, we find the magnification of the thin diverging lens is about 1/3, which would result in a reduced size image, and this agrees with our drawing. Here we talk about spherical refractive surfaces. First we have a convex hemispherical surface. As you can see, an image is formed inside the lens. The image is on the same side as the outgoing light, so it is a real image. The position and size is determined by the relation of the curvedness of the sphere side and its index of refraction of the material. The equation for spherical surfaces is given by equations 3 and 4. The radius here is positive for objects facing the convex side of the refractive surface. Here the object is inside the material with an index of refraction greater than that of the surrounding. We still use the same formulation, but we take note of the sign convention for its radius. Since the object is facing the concave side of the sphere, then its radius is negative. Here we have samples on spherical refractive surfaces. A cat is watching a goldfish in a spherical fish bowl of radius 15 cm. The goldfish is 5 cm from the side of the bowl nearest the cat. How far from the side of the bowl does the fish appear to be to the cat? For water, the index of refraction is equal to 1.33. First we draw the problem. It appears that the light rays will be coming from the bowl then into the eyes of the cat as an observer. We take into consideration the radius, which will be negative since it is on the side that faces the convex surface of the refractive material. The indexes of material are assigned as Na of the material and Nb for the surrounding environment, which is air, so N equals to 1. So we use equation 3 with the conditions for the scenario where index B is less than index A and radius is a negative. Rewriting the equation to solve for the distance of the image as perceived by the observer. We get that it is about 4.1 cm as perceived by the cat. Taking a closer look at this by examining its magnification, and we do this using equation 4. Substituting the values, and we see that its magnitude is a positive 1.1. This suggests that the image is larger compared to the object. This image is also on the opposite side of the outgoing light, thus it is considered as a virtual type of image. Here we have a concave hemispherical surface. Its shape is opposite to that of the convex surface. We see that the image formed is on the opposite side as the outgoing light. This image is considered a virtual image. The size and position is also determined by the properties of the concave material. Equations 3 and 4 are used to determine the relationship of the distances and magnification. Same sign convention is applied here like in the convex hemispherical surface. When the object faces a convex refracting surface, the radius of curvature r is positive. When it faces a concave surface, r is negative. Lens-maker equation is used for lenses that are not the same as thin lenses. In this case, we have a lens having two different curvatures as shown on the figure. So the lens would appear asymmetric. To calculate the property of such a lens, we use the lens-maker equation as shown by equation 5. The lens-maker equation incorporates the index of refraction of the lens. Note that this equation is for the environment to be air with index of refraction of 1. The sign of the radius depends on the position of the center of curvature. Radius is negative if its center of curvature is on the right side. And radius is positive if its center of curvature is on the left side. Here we have a sample problem on the lens-maker equation. Find out the focal length of the lens whose refractive index is 2. Also, the radius of curvatures of each surface is 20 cm and -35 cm respectively. We directly use the lens-maker equation and substitute the known values, and we get that the focal length of this lens is about 12.73 cm. Here we have a summary of the equations used from plane surfaces to curved surfaces for both mirror and lenses. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Diyes Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening, and see you next module.